Hello and once again welcome in this MOOC course on control system. And today's topic for the discussion, in today's class topic for the discussion is block diagram reduction technique. Block diagram reduction techniques. This is very useful topic in university exam as well as in competitive exam. Questions will be based on this method. We have already described the control system as a combination of control system is basically combination of components, combination of various components, combination of various stages or combination of various components. And these components are connected together to perform some operation when we apply the input signal. So the combination of components or various stages, or we can say, or various stages of control system make the overall system as complex system. This is in fact complex system as it is combination of various components or various components or stages are connected together. So overall, if we see the entire system, that is obviously a complex system. And if we are going to find out the overall transfer function, and if we are going to find out the overall transfer function for such complex system, overall transfer function for such complex system, then method would be very tedious, in fact difficult also. So in block diagram reduction technique, in this approach we will represent the stages by using block diagram. Various stages will be represented by block diagram, and all these blocks are connected together. All these blocks are connected together having its own transfer function. Suppose this is first stage, this is stage number 1, this is stage number 2. So we are representing with the help of block diagram and individual stages of control system that is complex in nature. So we are representing stages by using block diagram, and obviously that individual stage has its transfer function. Say for example, transfer function for this first stage is G1s, and for this second stage is G2s. So all these blocks are connected in this manner, representing individual stage by block diagram. So we will find, in this way we can find out the overall transfer function by using some rules for reduction of such block diagram. So in today's class we will discuss terminology used for block diagram and some rules that will be useful to reduce the complex stages in a simple form so as to make it convenient to determine the overall transfer function of control system. So this is the objective of today's class. We have to study the rules for block diagram reduction. Rule number 1. This is rule number 1. I will also cover some terminology relating to this topic also. The block diagram relates the output and input as per the transfer function relation. Suppose this is a block, this is a block in which standard input is RS, and this block will represent the stage of control system. So this block will relate the input and output quantity by this transfer function, which is defined as output quantity in Laplace transformed form CS, that is CS, to input quantity RS. This is the simple transfer function. This is the transfer function which is relating output quantity CS and RS. This is the fundamental. This is the basic for any block diagram representation. The transfer function is given by ratio of output variable to input variable. Or from this, we can find out the output in this way. This GS is multiplied by input RS. GS is transfer function of the system. So this is the representation of any individual stage of control system. That is the combination of so many stages. Second point is takeoff point. Takeoff point. We should know this terminology, especially in this case, block diagram reduction technique. This takeoff point is a point. This can be represented by this diagram. Suppose this is the point which is recognized as takeoff point. This is A, and from this is input RS. This is input RS. So this is one stage with transfer function G1S and corresponding output is C1S. From this point A, we can also provide the input RS to another stage with transfer function G2S, producing the output C2S. So this point A, from where we can apply the input to one or more stages without altering the input signal, is known as takeoff point. Without altering the input signal, this is called takeoff point. The point from where we can apply the input to one or more stages without altering this input signal RS, then it is called takeoff point. This is called takeoff point. Third one is blocks in cascade. Cascade means we have output of one stage is given as input to another stage. Then we can say that all these stages are in cascade. In amplifier case, we cascade so many amplifiers in order to produce high gain as the final resultant signal. So blocks can also be connected in cascade. Say for example, input signal is RS. This input signal is given to stage with transfer function G1S. This is output of this stage is C1S. Say for example, output is C1S. Now this C1S is input to the block with transfer function G2S. Similarly, this can be continued for next stage with transfer function G3S, and finally we have output, that is CS. So C1S is the input from first stage given to second stage, and in similar manner this output C2S is now input for third stage. So such connections of blocks is forming the cascade. So this can be this arrangement can be represented in this manner also. We can draw the equivalent of this cascading in this way. Transfer function G1s, G2s, and G3s. G3s can be combined to produce the final output CS. This is the equivalence of this cascaded stage. These are in cascaded stage. Cascaded stage. So this can be represented by this combination. So how we can find this output of this stage? First stage, if we take output as C1s, input for first stage is RS, and transfer function for first stage is G1s. Similarly, for second stage, output is C2s. Now for this second stage, output is taken from first stage. Input is taken as output of first stage, that is C1s. So this is G2s, and similarly for last stage, output is CS and input is C2s, that is the output of second stage. This is G3s. So overall, so these are the output of various transfer function of all three stages connected in cascade. So these can be multiplied. So these can be multiplied as C1s upon RS into C2s upon C1s and CS upon C2s, that is equal to G1s into G2s into G3s. So this is the overall transfer function, that is the ratio of final output to input to first stage, and this is equal to G1s, G2s, G3s. So we can replace all the cascaded form. We can replace the cascaded form by this diagram. So this stage, blocks connected in cascade form can be replaced by single block with transfer function of multiplication of individual stages, and this is given by CS upon RS, that is the multiplication of all three stages. This is the concept of cascade. So in block diagram reduction, this will be used frequently. If so many blocks are connected, then we will replace these blocks by single block diagram with relation having relation of output and input given by this CS upon RS is equal to this. So this is the blocks in cascade. Next one is summing point. Next one is summing point or junction point, we can recognize it. Summing point. If one input is RS and this is given to a point that can combine so many inputs. Suppose this is algebraic sum is positive, then another input is XS, this is also positive, and one input is YS, this is suppose negative, then we can find the final output CS, that is input RS plus XS minus YS. It means we can combine the inputs at this point considering their algebraic sign. So this summing point represents summation of two or more input signals entering in a system. So this is the summing point. This is called the summing point. summing point. This is the summing point, or output of summing point being the sum of the entering inputs. All these inputs are entering at this point. So we can take the output CS as the sum of individual input signals. This is simply, we can compare it with KCL, Kirchhoff's current law. Kirchhoff's current law. Summing point is the point which represents the summation of two or more inputs entering in a system. That is similar to KCL, where we can take some point as this is point P, this current is I1, this is I2, suppose this is entering current, these currents are leaving current, I3 and I4. Then we can I1, I2 minus I3 minus I4 at node is equal to 0. Summation of all currents are 0. Similar concept is similar to this. In case of control system, we will use summing points for the purpose of combining the inputs entering in a system, considering their algebraic sign also. Either it is positive or negative one. So next rule is related to summing point. This is the summing point, and we can interchange the position of summing point. This is illustrated in this point number 5. Suppose this is input RS. This is summing point where we have two inputs. One is RS and second is XS. And another summing point is available here. To this, one input is YS, sign is minus, and this is plus. So we can take the output here. That output is sum of RS plus XS minus YS minus YS. So output can be written in this way. This is the final output. That is the sum of RS, XS. Both are positive input. At this second summing point is also available. To this second summing point, one input is combination of RS and XS, and second input is YS with negative sign. So overall output is sum of RS plus XS and minus YS. Now it is also possible to shift this summing point here, or we can shift this first summing point at the position of second. It is the basically interchanging of summing point. So this is basically interchanging of summing point we can interchange the summing point. Positions can be interchanged. So this will, if we interchange, so this is input RS, take the second summing point with input YS having negative sign. This sign is positive for RS, and first summing point can be moved here with input XS having plus sign. So we can find the sum in this case RS minus YS. This is the these are the signals combined at summing point 1, and RS minus YS is applied to this summing point number 2, and second input for this is XS. So we can write down in this way. Output in both the case is constant. So this is possible to interchange the position of summing point if there is no effect on final output. So it is possible to interchange using this criteria. There should be no change in the final output, then it's possible to interchange the position of summing point. So this is the interchanging of summing point. Next rule which is applicable for reduction process of blocks is blocks in parallel. Blocks in parallel. So suppose we have one block with transfer function G1 as, second block with transfer function G2s, next block with transfer function G3s, and outputs from all three blocks are combined here at summing point, that then final output, suppose all these in outputs from these blocks are positive, and final and input to these blocks in parallel is rs, then this can be represented in this way. Input is rs, then at summing point we can combine all the inputs, then G1s plus G2s plus G3s, and final output is CS. So this is the equivalence in parallel. Blocks in parallel. If given blocks are connected in this manner, connected in parallel, then we can combine the outputs from different blocks at a summing point, and instead of using individual blocks G1s, G2s, and so on, we can represent by the single block diagram, and transfer function for this block diagram is sum of individual transfer function of blocks connected in parallel. So this can be connected in this way. So this is the blocks in parallel. This is rule number 6. We can also verify this. This can also be verified as in this final output is CS. This is the CS final output at this summing point. This CS is combination of outputs coming from here. Suppose this is so what at this stage output is input signal RS multiplied by its transfer function G1s. Similarly, RS is common, so RS is taken as input, and to produce the output, this is multiplied by transfer function of second stage, and for third stage RS, this is multiplied by G3s. So these are the corresponding outputs. These are the corresponding outputs produced from each individual stages, and these outputs are combined here. So final output is RS can be taken out as common, and this is G1s plus G2s plus G3s. This is the or this can be written in this way: CS upon RS is equal to G1s plus G2s plus G3s. So this is the overall transfer function. This is the overall transfer function or equivalent transfer function. Overall transfer function, we can say transfer function for blocks connected in parallel. If blocks are connected in parallel, then instead of using three blocks, we can represent this arrangement by equivalence having the transfer function of sum of individual transfer function. Input is Rs and final output is Cs. So overall transfer function is Cs upon Rs. That is equal to G1s sum of individual transfer function G1s, G2s, and so on. This can be extended for other stages also. So this is the blocks in parallel. Now, shifting of a takeoff point. We have already discussed the shifting point, takeoff point. Shifting of takeoff point. Takeoff point is point from where we can apply input signals to one or more system. That is called takeoff point. This takeoff point can be shifted. How this shifting can be made possible? Suppose input is Rs. From this point A, input is applied to a block with transfer function Gs. Resultant output is Cs. And from this A, this is given to another system. So obviously output is Rs. Now it is possible to move this shift point here. Suppose this is point B. So we are going to perform A to B. We are moving this takeoff point from position A to position B. Simple concept is that output should remain constant. Before and after the shifting process, output should not change. If output is Cs, this Cs is Rs into Gs, and here output is Rs. Output is Rs. Now this shifting, now this takeoff point has been shifted. So this is Gs. This is Gs. And takeoff point has been shifted from this position A to some position B at this point. Still, this is producing Rs into Gs. Output is Rs into Gs. Now takeoff point has been shifted at this position. So previous output was Rs. So in this case, output is Rs into Gs. If we check the output, then it is Rs into Gs. But it should remain Rs. Even after shifting from point A to B, it should not change. So in order to keep the previous output unchanged, Gs should be eliminated from here. So how this Gs can be eliminated? So we introduce a block diagram with transfer function 1 upon Gs. If we introduce one block in the path of this takeoff point, in the middle of takeoff point, with transfer function 1 upon Gs, then this input to this is Rs into Gs, Rs into Gs, and what should be the output? Rs into Gs is multiplied by 1 upon Gs, so this will give Rs only, this Gs will get cancelled. So shifting of takeoff point is also possible, keeping in mind that the output should not change after the shifting process. So in this case, we have introduced one additional block with transfer function 1 upon Gs. So this will give the final output Rs, which was in the case which was previously present before the shifting process. So RS should not be, output should not be changed. Simple concept is that RS should remain constant in this shifting process. This it is also possible to move this takeoff point from B to A. So in next case, suppose this input RS is given. This is takeoff point A. This is block with transfer function GS. This is point B. Output is CS. Here we are getting the output, that is also CS. And now we want to move this takeoff point from this position to this. Now we are going to perform shifting from B to A. So this shifting is possible if output at this point and this point don't change. We have to keep these outputs as constant. So this shifting is possible. This is point A, GS. This is the output is CS. Output is CS. This is point B, which is now shifted here. So this is, we should get output CS. We should get output CS. This is input RS. This CS is equal to simply multiplication. This is simply multiplication of RS and GS. RS and GS. And here also we are getting the same output, RS into GS. Now we have shifted this takeoff point at position A. So what should be the effect? So previously we were getting CS into RS, CS into RS. Sorry, we are getting here CS. Sorry, this we are getting here CS. So CS would remain constant. Now the output. Now this RS is. Now this is shifted to RS. Now this value is shifted to RS because we have shifted this point B at A. So this A is directly connected with input signal. So now output is shifted to RS. So RS. So we should get CS. So to do so, an additional block is introduced here in the path of this takeoff point, and transfer function is GS. So GS, yes, so this is CS, yes, GS. So RS is input, RS and GS. RS, if we introduce this this block with transfer function GS, then instead of RS we will get RS into GS. It means this is equal to CS. It is equal to GS. Once again we understand this. Previously in this first case, takeoff point was at B. So output is CS. If we move this takeoff point at position A, then output should not change. Then it is possible. If output doesn't change, then it is possible to move takeoff point from B to A. Now we have shifted this B to A. So in this case, output is CS. If we don't include this this block, then output is RS, which is the violation from this case. So we have introduced additional block with transfer function GS. So output of this block is input signal multiplied by transfer function GS, that is the RS and GS, which is nothing but output CS. So in this case also we are getting CS. Previously output from of this takeoff point was CS. So it is possible to move. It is possible to move takeoff point. It is possible to shift the takeoff point. Only thing we have to consider is that output should not change. So we should do something. And in this case, what we have done, we have introduced this block weight transfer function GS, which will provide the output as RS and GS. So out, which is equal to output CS. So in this class, we have covered 7 rules for block diagram reduction. So with this, I conclude this today's class on this control system. In next class, we will cover remaining points for the block diagram reduction technique. Thank you very much.